My name is Salman, and I'm a PhD scholar at OSA University of Southampton. And today I'm going to talk about holographically fabricated place gratings for out-of-plane focusing in integrated optics. Here's the outline of my talk, which includes motivation, and that is building the large area mode couplers for integrated optics. Then I will talk about edge grating couplers and their limitation for the scaling of large area devices. And then I will introduce direct UV writing as an alternative approach. And finally, I will go through some fabrication and characterization of out-of-plane place grating coupler. So silicon-based edge grating couplers are widely used in integrated optics for providing free space beams and interact with optical systems. So they have been really good, but up to the size of 100 microns. And they need extremely high fabrication accuracies in terms of grating period and waveguide thickness. Additionally, during the fabrication process, phase errors due to etching lead to the phase errors and limit the scaling to the large area devices. So here we come up with an alternative approach, which is using a blaze grating technique to provide a free space beam. And we are going to do it by using direct UV writing technique in silicon platform. So there are two aspects of this work. One is targeting large beams to 10 millimeter, and the other one is getting out small and focused beams. Compared to edge gratings, UV writing offers low change in refractive index, but better phase accuracy of large area devices. So we are going to do it on silicon platform. So this is our flame hydrolysis deposition system, which is used to deposit silica soot, and that we can dop with germanium and boron to enhance the photosensitivity. Later on, the deposited soot is stuck inside the furnace at a temperature of 1200 degrees Celsius for a nice consolidated glass formation. That is a typical structure which we use for our planar optics. Silicon, it got thermal oxide layer, and at the top of it, we deposit core layer, which is usually germanium and boron doped. And it's a photosensitive layer where we use it for UV writing. And on the top is the cladding layer. So our group has been doing a lot of work related with integrated optics for the last 20 years. And we are doing it by using 244 nanometer laser, which relies on the photosensitivity of doped silica. So here's our UV writing system, which got 4-axis air bearing stages and beam splits into 2 arms. And one arm of the interferometers pass through electro-optic modulator to control the phase. And then both beams are focused and generate the interference pattern inside the core layer. So here's the advantage of this UV writing system that provides a simultaneous fabrication of waveguides and gratings in a single step. There is another advantage of a phase control system to get a full control over the return grating period. That means more complex kind of grating profiles, such as Gaussian oxides and chirped gratings, can be formed via only software control. So for last few years, we have got a new laser system, which is a pulse laser, 5th harmonic solid state laser. And the pulse duration is 7 nanoseconds, got a longer coherence length to 1 meter, and it's robust, got less power instability and low maintenance. And we have recently demonstrated the waveguides and back gratings in doped planar silica, and it turned out to be a promising alternative for conventional longer wavelength laser sources. So now, moving forward to our main goal. So with this interferometer, we can introduce grating planes perpendicular to the chip, and we usually characterize in reflection using this system by using the optical spectrum analyzer and iridium doped fiber amplifier source. But for an out-of-plane grating coupler, what we need to rotate the grating planes at 45 degrees. That means we have to design a new interferometer which interferes at 45-degree angle. However, in this case, dual beam interferometry becomes impractical due to high Fresnel losses in the beams. So now the possible solution is a use of prism. The idea of the prism was presented 25 years ago for recording volume gratings in the polymer films. So with the use of prism and a few hundred micron layer for the index matching, we can get rid of Fresnel losses, and the both beams interfere inside the core layer to generate 535 nanometer grating period to match and couple out 780 nanometer laser out of the plane. That is the actual photograph of the system. So this whole system is stationary. Prism is stationary as well, but we can translate the sample around using the air bearing stages. So this is some comparison of Fresnel losses and the specific beam angles which we need, and they're going to interfere inside the core layer. So using this technique, we have fabricated channel waveguides and blaze gratings with uniform and Gaussian anodized profile. So moving forward to the actual characterization. So this is our fabricated chip. This is the photograph on the characterization system, which is aligned with the fiber pigtail, and we are launching 780 nanometer laser source inside the waveguide. It got 3 uniform gratings, and this photograph was taken by using IR sensitive camera. So you can clearly see 780 nanometer laser is coupling out of the plane. And in figure B, you can see the actual characterization of the beam coupling out using the Spiricon beam gauge camera. So this one is the uniform grating, and this one is the Gaussian anodized grating. You can clearly see the difference. Intensity is maximum here and decaying exponentially on surrounding. So this was for large area beams. Now another aspect was to get a focus beam using the chirped blaze gratings. You can find the details of chirp and focal length in this paper. And additionally, my colleague Tom is going to present his poster at 10 a.m. This is some characterization. So we have taken a height scan using the beam gauge camera, and you can see the figure A is the characterization of the focusing. So the chirped blaze gratings is going to provide the focus only in one dimension, and in the other direction, it's going to just diffract out. And that's what we are saying here. It's focusing here, distance along the waveguide, and it's going to just diffract out in the other direction. So it was the first device we have ever wrote, and we didn't take into account the surface refraction. For the next device, we considered the surface refraction in our software control. So you can clearly see we targeted the focal length 5 millimeter, and it's nearly 5 millimeter here, where the chip focus is at 0. And you can see it's just diffracting out in the other axis. So as a summary, we have first demonstrated the out-of-plane blaze grating couplers using direct UV writing approach. So compared to H gratings, efficiency is low. It's less than 10% for 3 millimeter long gratings. So currently we are looking to increase the efficiency. Here's our group, Optical Engineering and Quantum Photonics Group, which is one of the largest group at ORC, University of Southampton. And we are working in various dimensions from quantum technology, single photon detectors, sensing and telecom, plane waveguides. You can find the details on our website. And that's all. Thank you for being here.